Have a nice time. In the last class, we were proving the theorem. Any integral domain D can be enlarged to a field F such that every element of F can be expressed as the quotient of two elements of D. Such a field F is a field of quotients of D. So, given an integral domain D, we have to construct a field of quotients of F. And the construction includes 4 steps. First step is we have to define the elements of F. And second step, we have to define the binary operations of addition and multiplication on F. And in the third step, we have to check all the field axioms to show that F is a field under these operations. And finally, we have to show that F can be viewed as containing D as an integral domain. In the last class, we will discuss the first 2 steps. That is, we defined the elements of F. For that, first of all, we take the integral domain D. Then we consider the set D cross D, which contains set of all ordered pairs A, B such that A, B belong to D. Then we take a subset of D cross D as S, which is equal to set of all A, B belongs to D cross D such that B not equal to 0. After that, we define an equivalency relation on the elements of S in such a way that the element AB is equivalent to the element CD if and only if AD equal to BC. And we showed that this relation tilde is an equivalence relation on S. Therefore, this relation partitions the set S into disjoint equivalence classes. And we represented the equivalence class containing an element AB as the equivalent class containing AB in this using this notation. And we take the set F as set of all equivalent classes AB such that the ordered pair AB belongs to S. That is where we take each of the ordered pairs of S and where we take the equivalent class containing that element. So that equivalent classes constitute the set F. So this was the first step of the theorem. Now we have to show that F is a field. For that we have to define 2 operations on F. So we defined the operation addition in this way. We take 2 elements, equivalent class containing AB and the equivalent class containing CD, and the addition is defined as is equal to the equivalent class AD plus BC, BD. The reason for defining in such a way has explained in the previous video, and we defined the multiplication of elements in such a way that equivalent class AB into equivalent class CD equal to the equivalent class ACBD. And in the last video, we showed that these 2 operations, addition and multiplication defined here are well-defined operations also. Now, 2 more steps remains. We have to show that all the field axioms are satisfied by the set F together with the operations, additions and multiplication defined by us. And finally, we have to show that F can be viewed as containing D as an integral domain. We are discussing these 2 steps in this video. So, we are going to show that F satisfies all the field axioms. And what was a field? A field is a commutative ring with unity in which all the non-zero elements are units. And we can classify all the properties of a field in 2 groups. First set is F with addition is an abelian group. For that, we have to show the 5 properties here. First one, addition is binary in F, addition is associative, there exists additive identity element in F, F contains additive inverses of all of its elements, and since F plus is an abelian group, addition is commutative in F. All these properties together, we can say that F with addition is an abelian group. Now, with respect to multiplication, the second set involves these properties. Multiplication is binary in F, then multiplication is associative in F. Actually, it is a property of a ring. Then there exists unity in F, that is F contains the multiplicative identity because F is a ring with unity. Then all non-zero elements of F are units. That is, all non-zero elements of F has multiplicative inverses in F itself. Finally, since F minus zeros with multiplication is an abelian group, multiplication is commutative in F. So we have to show these 10 properties to show that F is a field. So let us check the properties one by one. We have defined the addition and multiplication in this way. AD plus CD equal to the equivalent class AD plus BC, BD, and the equivalent class AB into equivalent class CD gives equivalent class AC, BD. So first of all, we have to show that these operations addition and multiplication are binary operations in F. Elements of F are the equivalent class of the ordered pair AB, where ordered pair AB belongs to S. And for an element AB to be belong to S, the condition is that B not equal to 0 and A comma B are elements of the integral domain D. So we have to check whether these results AD plus BC comma BD and the equivalent class ACBD belong to the field F. We know that the elements A, B, C, D are all elements of the integral domain D. Clearly, AD plus BC, AC and BD are all elements of D. And we have taken the element AB and CD as elements of S. Because the equivalent class AB and equivalent class CD are elements of F as we taken here. Therefore, clearly the ordered pair AB and ordered pair CD belongs to S. Since these elements belongs to S, we may conclude that B not equal to 0 and D not equal to 0. For an ordered pair to be an element of S, second coordinate not equal to 0. So here B not equal to 0 and D not equal to 0. And here D is an integral domain. For an integral domain, when we multiply two non-zero elements, the product becomes also not equal to 0. So here we see that in our definition of addition and multiplication, second coordinate is B into D. So here we got that BD not equal to 0. Therefore, AD plus BC comma BD is an element of S and ordered pair ACBD is also an element of S. So clearly these equivalent classes belongs to the set F. Therefore, we can conclude that addition is binary in F and multiplication is binary in F. Now let us check whether addition is associative in F. Now let us show that addition is associative in F. For that we take two elements of F, equivalent class AB, equivalent class of CD and equivalent class of EF. And we consider in the equivalent class AB plus the sum of equivalent classes of CD and EF. So we have to perform this addition first. So CD plus EF gives CF plus DE comma DF. That is written here. And now we have to add the equivalent class of AB plus the equivalent class of CD, CF plus DE comma DF. For that we have to multiply A with DF plus B with the CF plus DE. So here we can apply the properties that multiplication is distributive over addition since D is an integral domain and all these elements A, B, C, D, EF are all elements of D. Therefore, we can use the result that multiplication is distributive over addition. So we can multiply the elements as usual. So we may write A DF plus B CF plus B DE, comma. Now we have to multiply the second coordinates D into DF. That is a result here. Similarly, if we add the first two equivalent classes together, then we get equivalent class AB plus equivalent class CD gives here AD plus BC, comma BD. Now we have to add this together with the equivalent class EF. So what we get? AD plus BC into F. That is ADF plus BCF plus BD into E. That is BDE, comma. Now we have to multiply the second coordinates BDF. That is here. Now we may see that these two sums are equal. Therefore, addition is associative in F. Likewise, you may try to prove that multiplication is also associative in F. Now we are going to show that there exists an additive identity element in F and there exists a multiplicative identity element in F. So let us find the additive identity element in F. For that we will take an element AB belong to F and we have to find an element in F such that equivalent class of AB plus that element gives the result as equivalent class of AB itself. That element will be the additive identity element. So to locate that element, we just consider the case of set of all rational numbers which we had constructed using set of all integers. Consider a rational number A by B as the ordered pair AB. And what will be the additive identity element in Q? You know that 0 is the additive identity element in set of all rational numbers because if we take any rational number A by B plus 0 again gives us A by B. But we have to express this 0 as an ordered pair AB. And what will be the ordered pair corresponding to 0? We can consider 0 by 1. 0 by 1 is actually equal to 0 and it can be denoted as 0, 1. So let us check whether the equivalent class of 0, 1 becomes the additive identity element in F. So we just add equivalent class AB plus equivalent class of 0, 1. So what will be the sum? The sum is actually the equivalent class A into 1 plus B into 0, comma B into 1. So that what will be the result? This is equal to equivalent class B into 0 is 0, A into 1 is A. So we have A comma B. So this equivalent class 0, 1 acts as the additive identity element in F. But you may note that instead of all rational numbers, 0 by 2, 0 by 3, all are equal to 0. So we can denote the element 0 as the ordered pair 0, 2, 0, 3, etc. All these elements 0, 2, 0, 3, etc. belongs to the equivalent class of 0, 1. The element 0, 2 belongs to the equivalent class 0, 1 if and only if element 0, 2 is equivalent to the element 0, 1. If and only if, how we have defined the equivalency, the product of these two elements becomes equal to product of these two elements. So clearly 0 into 1 equal to 2 into 0. That is 0 equal to 0. So we see that all these elements 0, 2, 0, 3, etc. belongs to the equivalent class of 0, 1. So you can say that the additive identity element in F is either the equivalent class 0, 1 or the equivalent class 0, 2, etc. because all these equivalent classes are considered as equal elements in F. So for convenience, we consider the additive identity element in F as the equivalent class 0, 1. And here you may also check that AB plus 0, 1 equal to equivalent class AB, that's equal to the equivalent class 0, 1 plus the equivalent class AB. Therefore, additive identity element in F is the equivalent class 0, 1. Here remember that you cannot take the element equivalent class 0, 0 as the additive identity. Why? We had defined the elements of F as the equivalent class of ordered pair AB where this element B, second coordinate, not equal to 0. So we cannot consider the equivalent class of 0, 0 as the additive identity here. Okay. So the additive identity in F is equivalent class 0, 1. Now we have to find the multiplicative identity element in F. For that, as in the earlier case, we will take an element AB belong to F. Multiplicative identity element is that element in F such that when we multiply with an element in F, it will result the element itself. So to find that element, as in the previous case, we will consider set of all rational numbers. What is the multiplicative identity element in Q? We know that it is 1. And we may denote the rational number 1 as 1 by 1 or 2 by 2, 3 by 3, etc. So first of all, we will take the first element. So 1 by 1 may be denoted as the ordered pair 1, 1 in our case. Therefore, we will consider the equivalent class of 1, 1 first. So we have equivalent class AB into equivalent class 1, 1. What will be the product? The product is defined in such a way that we have to multiply A into 1, then B into 1. That is equivalent class AB itself. So we may conclude that 1, 1 is the multiplicative identity element in F. And what about the remaining elements 2 by 2, 3 by 3, etc. here? We can show that the ordered pairs 2, 2, then 3, 3, etc. all belongs to the equivalent class 1, 1. Because the element 2, 2 is actually equivalent to the element 1, 1. Because 2 into 1 equal to 2 into 1. Therefore, these elements 2, 2, 3, 3 all belongs to the equivalent class 1, 1. In other words, these pairs 2, 2, 3, 3, etc. are equivalent to the pair 1, 1. So, viewing as elements of F, equivalent class 1, 1, equivalent class 2, 2, etc. are all equal. For our convenience, we will consider equivalent class 1, 1 as the unity element in F. Therefore, unity or multiplicative identity in F is equivalent class of the pair 1, 1. Now we are going to show that F contains additive inverses of all of its elements and also F contains multiplicative inverses of all the non-zero elements of F. For that, we take an element A, B belongs to F. We have to find the additive inverse of AB and we have to show that that element belongs to F. Additive inverse of AB means that it is that element in F when we add with equivalent class AB results to the additive identity of F. And what is the additive identity of F? We have already showed that the equivalent class of 0, 1 is the additive identity of F, or it can be denoted as equivalent class 0, 2, 0, 3, etc. For example, equivalent class 0b for any b becomes the additive identity of F. For our convenience, we are taking here as equivalent class 0, 1. And what will be the element when we add with equivalent class AB results to the equivalent class 0, 1. To find that inverse, we will again consider our example of set of all rational numbers. We will take a rational number A by B, where B not equal to 0. And what will be the additive inverse of A by B? It is actually minus A by B, because A by B plus minus A by B results to 0, which is the additive identity in Q. So naturally, the additive inverse of equivalent class AB may be the equivalent class minus A comma B. Let's check what happens if we add equivalent class AB with equivalent class minus A comma B. And the addition is defined in such a way that we have to take the product of these two elements A and B plus the product of B and minus A. So that becomes the first coordinate becomes AB plus minus BA comma B into B. That will be denoted by B square. Now this is equal to the equivalent class AB plus minus AB comma B square, since multiplication is commutative in D, is equal to the equivalent class 0 comma B square. Thus, when we add the equivalent class of minus AB with the equivalent class of AB, the result is the equivalent class 0 comma B square. We may note that the element 0 comma B square is equivalent to the element 0, 1, because 0 into 1 equal to 0 and B square into 0 equal to 0. Therefore, this equivalent class 0 comma B square is equal to the equivalent class of 0, 1. Now we have to verify that this element equivalent class minus A comma B belongs to the field F. Clearly the element minus A comma B belong to S, because we take the element equivalent class AB belong to F. Therefore, B not equal to 0, and also since A belong to D, minus A also belong to D. Therefore, this element minus A, B belong to D cross D, and also B not equal to 0. Therefore, minus A, B comma B belongs to S. Which follows that the equivalent class of minus A comma B belongs to F. Therefore, the additive identity element of the equivalent class AB becomes the equivalent class of minus A comma B, since the sum of these two terms results the additive identity element 0, 1 in F. Now we are going to show that all non-zero elements in F are units. That is, F contains all the multiplicative inverses of non-zero elements in it. So we take an element AB, which is a non-zero element in F. And what happens if the element A equal to 0 in D? If A equal to 0, then this element equivalent class AB becomes equivalent class 0B. And we have already showed that this is equal to the equivalent class 0, 1. Since the element 0B is equivalent to the element 0, 1. And the equivalent class 0, 1 is the additive identity element in F, which we have referred as 0 in F. Here we have taken an element AB, which is a non-zero element in F. Therefore, A equal to 0 is not possible here. So we have, if we take an element AB, which is a non-zero element in F, A is not equal to 0. So we will think of the element BA in F, because an element in F is an ordered pair AB which belongs to D cross D such that second element is not equal to 0. Here we showed that A cannot be 0, therefore the equivalent class BA belongs to F. Now we consider the product of AB and BA. As per the definition of a multiplication, we have to do the product of first two coordinates, then product of second two coordinates. So the answer becomes equivalent class AB comma BA. And since D is an integral domain, multiplication is commutative there. So we can write this element as AB comma AB. And this is actually equal to the equivalent class 1, 1. Since the element AB comma AB is equivalent to the element 1, 1. Because AB into 1 equal to AB into 1, because these two elements are equivalent. So we may say that the equivalent class of AB is equal to the equivalent class of 1, 1. And the equivalent class of the element 1, 1 was the multiplicative identity in F. So we showed that when we multiply the equivalent class AB with the equivalent class BA, the result becomes the multiplicative identity in F. That means that multiplicative inverse of the equivalent class AB is the equivalent class BA. In the case of rational numbers also, we can check whether the result is matching. We take a rational number A by B which belongs to Q, and we are taking here A not equal to 0, and what will be the multiplicative inverse of AB, A by B? It is B by A. Since A not equal to 0, B by A also belongs to Q, and A by B into B by A is actually equal to the multiplicative identity 1. So from here also we can easily note that the equivalent class BA becomes the multiplicative inverse of equivalent class AB. So we showed that F contains additive inverses of all of its elements, and all non-zero elements of F are units. And the last one, addition is commutative in F and multiplication is commutative in F are easy results. I think it can left it for you to work. Thus, F together with the addition and multiplication we defined here satisfies all the field axioms. So we can conclude that F is a field. Thus, the third step of our theorem is also complete. Now it is enough to show that F can be viewed as containing D as an integral subdomain. I think it is better to prove in the next video. Let us stop here.